In this exercise, we look at annuities, we have to calculate premiums, look at the profit, look at the standard deviation, and make sure that with large probability we have a profit when many of these annuities are sold. So starting with question A, we have to calculate the premium. So what is the setting? We are selling annuities to men aged exactly 60, and each policyholder pays a single net premium, P. So it's a single premium, and it's important. So after that, he receives an annuity of 30,000 a year in arrear. So at the end of the year, the first payment is made. So let us think about what this notation for this annuity would be. So P is the premium, and we have to calculate it, and we want to use the premium equivalence principle. But for that, we need to have the expected present value of the annuity. So let us denote by AK60, selected age 60. So this is the annuity that is described up here. So this annuity, it's paid in arrear. And this is not official notation for some reason, but it is described in the subsection of the whole life immediate annuity in chapter 5. So, but it is given as the relation with the annuity paid in advance. So it's given by K60 plus 1 minus 1, because we do not pay in advance at the start of the year, but at the end of the year. So look at this in section 5.4.3 in version 2 of the book. If you have another version, check it out. But in any case, this is the running variable we want to look at. And using the equivalence principle, so let me call it the equiv principle, we get that the expectation of P, which is in this case just P, because P is a number, it's not a random variable, the expectation of P should equal the expectation of the benefits that outgo, so the benefits that go to the policyholder. And in this case, it's 30,000 a year, so we multiply 30,000 by the value of this annuity. And also note that we took select ages. We took select ages because in this chapter we assume the standard select survival model. So there's an interest rate of 5%, the force of mortality is Macomb's law, and the selection period is 2 years. In any case, so we have to account for selection. And then this is by definition equal to 30,000 times the expected present value, which is denoted A bracket 60. And then using the appendix D, which contains all the tables for these values, we can infer what A60 is. But we need a step in between because it doesn't actually show the value of A60, but it does show the value for A double dot 60. And it's related in this way, which can be seen by the random variables we introduced as well. And looking up the value, it gives you 13.913. And if you compute this, it should give you 417,390. Now note that this 13.913 is rounded off. So you might get slightly different numbers if you compute the actual value using the non-rounded numbers. But in any case, it should be around 417,400, let's say. And this is the value of the premium. So this solves part A. For part B, we need to calculate the probability that the present value of profit on a single policy is positive. Now let's think about what profit means in this setting. So we have profit if the amount that we receive, we as the life insurance company, is larger than the benefit that we have to pay. So if it is the case that P minus whatever we have to pay, which is in this case 30,000 times, okay, so the annuity, which is random, if this difference is bigger than 0, if this is bigger than 0, then we have a profit. So the question is, how can we find the probability that this is bigger than 0? That is what we have to solve. In this case, we look at the probability of profit to say what age must the policyholder maximally attain for us to make a profit. Now let me remove all of this. Then we want to compute the probability that P minus 30,000 times AK60 is bigger than 0. Now if we rewrite this, then we can say that this is equal to AK60, oh, I forgot the bar here, smaller than the 13.913. So that's the value that we looked up in the table. And then we rewrite this into the, so there's no formula, there's no immediate formula to rewrite this quantity, to rewrite this. So how to rewrite this using formulas that we know, we use the A double dot K60 plus 1, because for this one there are formulas known. So this gives us, we rewrite this as we saw in part A, this is equal to A double dot of K60 plus 1 bar minus 1 smaller than 13.913. And then, so we say this is equal to, and the formula is 1 minus V to the power K60 plus 1 divided by 1 minus V, and this should be smaller than 14.913. So I move the 1 to the other side. Okay, rewriting this gives us that this is equal to V to the power K60 plus 1 larger than 1 minus V times 14.913. So I subtracted 1 and I multiplied by 1. And then we use that, let me make a thought bubble, then we use that V equals e to the power minus delta, where minus delta is the force of interest. And we can find delta, of course, because we know V. And this gives us that, so this is equal to e to the power minus delta times K60 plus 1. And the right hand side did not change. Okay, then we want to isolate K60, which gives that this is equal to K60. Let's see, it's going to be smaller than, because there's a minus, but first we take the natural logarithm of both sides. Yes, so then we have this, and then we divide by delta, actually minus delta, and then we have to subtract 1. Ah, here's a 1, I forgot. All right, and so finally, if you plug this all in, this gives you that, this means that if the right hand side you can compute, because we know V, we know delta, and you can compute this right hand side. So this boils down to the probability that K60 is smaller, strictly smaller than 24.38. Now all that is left to do is to actually compute this probability. Now notice that this probability is simply a probability of death of the select life age 60 before living how many years. So it says probability of dying within 24.38, but k is the number of whole years lived. So we have to make sure that we keep track of whole years. So before living another 25 years, we need to round up. And we know that this is equal to 25q 60. So this is the probability of death for a 60-year-old to not live another 25 years. And we can rewrite this as 1 minus the survival probability. And using the standard assumptions of this chapter of the standard select survival model, we can compute this, and it gives us 0.36641. And now we finally computed the probability of profit. Now in part C, we need to compute the standard deviation of the present value of profit on a single policy. In B, we computed the probability, and now we compute the standard deviation. Now recall that the present value of profit is equal to, so it's equal to P minus 30,000 times this random variable that we introduced, AK 60, and that, but we actually rewrote this immediately using this A double dot, because we don't know any formulas for A60. So we rewrote this in this way, A double dot, K60 plus 1 minus 1. Okay, so this is the present value of profit, right? And now we have to compute the standard deviation. Well, in order to obtain the standard deviation, we know it's equal to the square root of the variance. So it might be useful to first take the variance. Okay, so let's do that. Let's define this as I don't know, let's call it x. So some random variable. Then the variance of x equals, so let me write it out completely for once. So 30,000 times a k60 plus 1 plus 30,000. And of course the variance of numbers, so the variance of p and the variance of 30,000, this will be 0, because the variance of a number is, there is no variance in a number. A number is just a number, it's not random. And we use that, we can take out this minus 30,000 out of the variance, so it's 30,000 squared, times the variance of this object, which is the annuity due for somebody aged K60 plus 1. Okay, and then let's use a formula. Let's use a formula for the one we used before for this annuity, and it was equal to 1 minus v to the power K60 plus 1 over 1 minus v. And similar to before, so we can take the variance of 1 minus v k60 plus 1, but we know that the variance of 1 will simply be 0, and we can actually take out this 1 minus v in the denominator. So this gives us 30,000 over 1 minus v squared times the variance of v to the power k60 plus 1. And this is in actuarial notation. So we have this constant, 1 minus v squared. And at times the second moment of this k60 plus 1 discounted minus the first moment squared. So now we have an expression for the variance, and these values we can look up in Appendix D, because we still assume the standard select survival model. And then the standard deviation is, so let's denote this as as d of x is the square root of the variance of x, which is then 30,000 over 1 minus v times the square root of this expression, so of the second moment minus the first moment squared. And plugging this all in should give you 97,201 approximately. And this is the standard deviation of the present value of profit on a single policy, which answers part C. For part D, we suppose that the office now sells 1,000 of such annuities simultaneously to independent lives, and then we have to compute a new value of the premium such that the probability that the present value of the profit to the insurance company is positive is 95%. So we want a 95% probability to make a profit. Okay, so how to go about this? We will use some probability theory and central limit theorem and some statistics. So let's denote, as in part C, we had the random variable x to denote the profit, but now we have x1 up to x1000 to be the present value of profit. So they are random variables with a mean equal to, for each xk, let's say, the mean is equal to some new value p, and we look at the difference with the value that we found in part A. And its standard deviation is what we computed in part C. Then we want to introduce a new random variable, which is the sum of all these x's, because we are selling it simultaneously to 1,000 independent lives. So y, a new random variable, is the sum of all these xk's, and using the central limit theorem, so by the central limit theorem, we know that y will approximately have a normal distribution with the mean being equal to 1,000 times the mean of x, and the variance also being 1,000 times the variance of x. So let's denote that as the variance of x1, let's say. Doesn't matter which one I do because they all have the same distribution. Okay, and we computed the standard deviation in part C, so this is what we'll use. Now recall that for some random variable, let's call it r. So if r is normally distributed with mean mu and variance sigma squared, then z, defined as r minus mu divided by sigma, this will have a standard normal distribution, and we will use that actually. So now we want to compute the probability, the value p, such that the profit is at least 95%, or is exactly 95%. To do that, we need to compute the probability that y is simply positive. So using this central limit theorem assumption, this implies that we can rewrite this as, so we use the CLT and the thought bubble at once, and it gives us that we have that this is equal to y minus its mean, which is 1000 times p minus 417,390 divided by its standard deviation, which is the square root of 1000 times the standard deviation of x, of x1, let's say. And this should be bigger than, okay, so this side we also have to subtract the mean. So have to subtract the mean and also divide by the same standard deviation. And this has to equal 0.95, and then we have to solve for p here. Now to do that, we use the thought bubble and say that this is approximately a random variable z, which is standard normal and bigger than this value. So minus 1000 p minus 417,390. And then the standard deviation here. And we know that, so again, we can look up this value in a z table. We know that the probability that z bigger than something equal than to 0.95 is actually z to, it should be minus 1.65. So you can look up this value in a z table, and therefore we only need to solve that this expression that we have in the probability is equal to, wait, let me actually write down the standard deviation of x because we computed it. So this was 97,201 approximately, and this should equal minus 1.65. Okay, so now we can solve for p, and this will give us that p is equal to 422,461. Yeah, okay, that's 0.7. And I may have made some rounding errors, or you may use a slightly different z-score, but it should be around, let's say, 5,000 more than what you found at A, because recall at part A, it's bigger than, so this, let's say the P from part A, which is the 417,390. So apparently if you charge about 5,000 more per policyholder, you have a 95% probability of profit. That's what we can conclude from part D, which finishes the entire exercise.